Hello everyone, this is Unprocessed Math. In this lecture, I will talk about antiderivatives and indefinite integrals. So let's get started by looking at a very simple example. So take the function x squared. If we differentiate this function, then the derivative will be 2x. Similarly, if you differentiate x squared plus 5, then the derivative will still be 2x. And the reason is that derivative of 5, which is a constant, is 0. So if I replace this number 5 here by any other number, by 100, by 7, by minus 200, any other number, still the derivative will be 2x. So this is how we generally how we look at the differentiation. Now, and you call a 2x the derivative of x squared. And now, what's x squared called? X squared called actually an antiderivative of 2x. So 2x is the derivative of x squared, and x squared is an antiderivative of 2x. And you see that antiderivative of the function is not unique. X squared plus 5 is also an antiderivative of 2x. So if you have one antiderivative, then you can add any constant to that antiderivative and still you will get an antiderivative. And the set of all antiderivatives of the function 2x is going to be actually of the form x squared plus some constant. And this is the way that we write this set of antiderivatives. And this is called the indefinite integral of 2x. So this is how it's written. We call it the integral of 2x or the indefinite integral of 2x dx, and it's equal to x squared plus c. Again, x squared plus c is the form of all antiderivatives of the function 2x, and that's simply what an antiderivative and indefinite integrals means. So this notation means the indefinite integral of 2x. And in order to find the indefinite integral, all you need to do is just find one antiderivative and add any constant. And this constant is generally called the constant of integration. So let's look at another example. Take the function sine x. If you differentiate sine, the derivative is cosine. Now, if you're looking for an antiderivative for cosine, which means that if I'm looking for a function whose derivative is cosine, one such function is sine, because the derivative of sine is simply cosine. And you know that we can add any constant to sine. So the derivative of sine x plus any constant is going to be cosine. So the indefinite integral of cosine x dx, which is basically the set of all antiderivatives of the function cosine, is going to be of the form sine x plus c. So the indefinite integral of cosine x dx, or sometimes you simply say integral of cosine x dx, is going to be sine x plus any constant. So it's simple. And if you know the derivative formulas for basic functions, you actually know the antiderivative formulas for those basic functions. Let's look at a few examples. So this is the example that we just saw. Antiderivative of cosine x dx is sine x plus any constant. Now, suppose now in the second example, we want to find the indefinite integral of sine x dx. So what does this mean? This means that I'm looking for a function whose derivative is sine. And you may say it might be cosine. It's actually cosine, but the point is that if you differentiate cosine, the derivative of cosine is not sine, it's minus sine. So I have to put the sign here so that if I differentiate a cosine, then I'll get a minus sign, and this minus signs will cancel that, and I will get sine. So antiderivative of an antiderivative for sine x is minus cosine x, and I can add any constant. So the indefinite integral of sine x dx is minus cosine x plus any constant. Another example is, let's say I want to find the indefinite integral of x to the power 100. I'm looking for a function whose derivative is x to the power 100. And you can check that if you differentiate x to the power 100 plus 1 divided by 100 plus 1, then the derivative will be x to the power 100. And you know that you can always add a constant because the derivative of constants are 0. Let's look at the next example. I'm looking for a function whose derivative is x cubed. If you differentiate x to the 4 divided by 4 plus any constant, the derivative of such function is going to be x cubed. So the indefinite integral of x cubed is x to the 4 divided by 4 plus some constant c. So you see that in both these examples, what we are doing is that we take the exponent, we add 1 to the exponent, and you divide by the same number. So antiderivative of x to the power 100 becomes x to the power 100 plus 1 divided by 100 plus 1. Same thing here. Antiderivative of x cubed is x to the power 3 plus 1, which is 4 divided by the same number. And that's a pattern that we're going to, again, see soon. So the next example, we are looking for an antiderivative for the function e to the x. You know from your differential calculus class that the derivative of e to the x is e to the x. So if you're looking for an antiderivative for e to the x, it's going to be simply itself, because if I differentiate e to the x, then the derivative will be e to the x, and you can add any constant. Next example, I'm looking for the antiderivative of the function 0. That means I'm looking for a function whose derivative is 0. Those functions can only be constant. So any constant, if you differentiate any constant, you're going to get 0. So the antiderivative of the function 0 is going to be a constant. So as I already mentioned, if you have derivative formulas, those derivative formulas already give you some antiderivative formulas. But we are going to list antiderivative formulas for some basic functions that are commonly used. So this is the one that we have already seen. If you have x to some power n, as long as n is not equal to -1, then the antiderivative can be simply computed by adding 1 to the exponent. So it becomes x to the power n plus 1 divided by the same number, and you can add any constant. You don't want n to be -1 because you don't want to be dividing by 0 here. Antiderivative of e to the x is e to the x. We have already seen this. If you have any exponential function, the antiderivative of a to the power x will be a to the x divided by natural log of a plus any constant. And you can simply verify this by taking the derivative of this function and simplifying. You'll see that if you differentiate this function, then you'll get a to the x. So the antiderivative of a to the x is going to be a to the x divided by natural log of a. And antiderivative of 1 over x is natural log of absolute value of x. And you see that this formula 4 is actually the formula 1 actually -1. So what you have here is x to the power -1. And the antiderivative of x to the -1 is simply natural log of x plus any constant c. Let's look at the next example. So here, the antiderivative of secant squared is tan, and this is simply because the derivative of tangent x is secant squared, and you can add any constant. antiderivative of cosecant squared is minus cotan. And this is simply because of the derivative formula that you have. The derivative of cotan is minus cosecant squared. So you put the minus sign here so that if you differentiate minus cotan x, you get cosecant squared x. And we have some other derivative formulas, antiderivative formulas, or they're also kind of derivative formulas. So if you want to find an antiderivative for secant x tan x, the one antiderivative would be secant x. And you can simply check the derivative formulas and see that the derivative of secant x is actually secant times tan. Similarly, antiderivative of cosecant times cotan is minus cosecant x. If you want antiderivative of any constant, is going to be the same constant multiplied by x plus c. And this is simply because if I differentiate this function, I will get a. And you have these two general formulas that antiderivative of sum of two functions is sum of the antiderivatives. Or the antiderivative of f minus g, if you subtract two functions and find the antiderivative, then it's equal to, then you can basically separately find the antiderivatives and subtract or add. If you have a constant multiplied by any function and you want to find the antiderivative of c times f, then you can simply put the c outside of the integral sign, and the indefinite integral of cf is going to be c times indefinite integral of f. Now you see we have these 11 formulas, and there are some more, and you may ask, it's a reasonable question whether you should sit down and memorize these or how to deal with keeping all these formulas in mind. And my suggestion is that you never try to sit down and memorize these. What you do is that after you have seen that there are antiderivatives formulas or for this kind of functions, so every time that you want to integrate a basic function, you go back to these tables, to this antiderivative formula tables, and you look at the formula, you spend a few seconds, think about it, and then move on. Never try to memorize them. Just think about it for a few seconds and move on. And you'll see that after you use them 4 or 5 times, you spend a few seconds each time, these formulas will stay in your mind without even trying. So don't be intimidated by these formulas. Just relax, and every time that you need them, spend a few seconds and move on, and you'll see that all these formulas will stay in your mind after a few times of using them. So let's look at another example. This is more concrete. So suppose I want to find the indefinite integral of square root of x. Always when you're dealing with radicals, with square root of x, cube root of x, things like that, it's always a good idea to write those expressions in terms of fractional powers. So square root of x can be written as x to the power 1/2. So what I'm trying to do, I'm trying to find an antiderivative for x to the power 1/2. And the way you can, now using the formula that I showed you here, this is x to the power n, but n in this case is 1/2. So all I need to do is to add 1 to 1/2, and we know that 1 plus 1/2 is actually 3/2. So the antiderivative of x to the 1/2 is going to be x to the power 1/2 plus 1, which is 3/2 divided by the same number. But instead of dividing by 3/2, you can actually multiply it by 2/3. And that would be an antiderivative for square root of x. Let's look at the next example. I have the integral of x squared 1/x minus 5 cosine x dx. All I need to do is to find an antiderivative for each of these three functions separately and add. Antiderivative of x squared is going to be, this is x to some power. So I need to add 1 to 2, so it becomes 3, and I divide by the same number. So the antiderivative of x squared becomes x cubed divided by 3. Antiderivative of 1 over x, this was one of the formulas that I mentioned earlier. That's natural log of absolute value of x. And if you want to find an antiderivative for minus 5 cosine x, minus 5 is just a constant. I'd put it aside. And an antiderivative for cosine, you know that it is sine. This is one of the formulas that we have already seen a couple of times so far. So, and you can add any constant. So this function becomes the indefinite integral of this function. Next example, I have x to the power minus 2 over 3, 5e to the x, secant squared. I have three functions here, and I integrate them one by one, add, and I will get the antiderivative for the whole function. So here I have x to the power minus 2 over 3, and so you know that you have x to some power, and in order to find an antiderivative, you need to add 1 to minus 2/3. And if you add 1 to minus 2/3, that's going to be 1/3. So the antiderivative of x to the power minus 2/3 is going to be x to the power 1/3 divided by 1/3. But if you're dividing by 1/3, it's the same as multiplying by 3. So the antiderivative of x to the power minus 2/3 is 3x to the power 1/3. Then, so I'm done with this function. Now I want to integrate 5e to the x. 5 is just a constant. Antiderivative of e to the x is e to the x. So antiderivative of 5e to the x becomes 5e to the x. I'm done with the second function. Now, the third function is secant squared. And if you remember from the derivative formulas that we saw earlier, antiderivative of secant squared is, an antiderivative is tangent. And I can add a c at the end, and that's the constant of integration. So the antiderivative of this function is this function given here for any constant c. Now let's look at a slightly different problem. These kind of problems are called initial value problems, where you're given some information about the derivatives of some function f, and you're asked to find the function f. In this case, I'm given the second derivative, the first derivative as 0, and the value of the function at 0. And from all these information, I'm supposed to find the function f. And you can solve this kind of problems by integration. The way we are going to deal with this is that I'm going to start with this formula. So I'm given the second derivative of f. I write it here. So I know that the second derivative of f double prime is equal to sine. So I'm going to integrate both sides of this equality. So the integral of f double prime is equal to integral of sine. And now, what does this mean? This is when so you want to find an antiderivative for f double prime. That means you're looking for a function whose derivative is f double prime. That function is f prime, because if I take a derivative from f prime, I will get f double prime. So the one antiderivative for f double prime is f prime. Another way to think about this is that when your integration and differentiation are actually they actually cancel each other. So when you find an antiderivative, you're basically anti-differentiating. So if you have an integral of f double prime, when you want to evaluate that, the integral sign is actually canceled will cancel one of these derivatives and you will end up with f prime. That's a simple way of keeping this in mind, that if you integrate f double prime, then the integration will cancel one of the primes, one of the derivatives, and you will end up with f prime. So an antiderivative of f double prime is going to be f prime. So I'm replacing this with that. And then we have seen this before. Integral of sine is minus cosine, because the derivative of cosine is minus sine. So I put this minus sign here so that when you differentiate minus cosine, you get sine. This is, again, you have seen this in the tables that I have shown you. But there, again, it's going to be a constant c. Every time that you integrate, there will be a constant. This is called the constant of integration. So we get that f prime is equal to minus cosine x plus c. Now I'm going to determine the c. And for that, I'm going to use this information here. I know that f prime of 0 is 3. It's given here. So what I'm going to do is that in this formula that I have for f prime, I'm going to substitute x's by 0. So you substitute x by 0, so you get f prime of 0. You substitute x by 0 here, so you get minus cosine 0 plus c. So you have 3 equals f prime of 0. This is given here. And I'm giving this by substituting x by 0 here. And if you do that, keep in mind that cosine of 0 is 1. So if you replace this by 1, you will get 3 equals minus 1 plus c. And if you solve it for c, you will get c equals 4. So if you go back to this formula that you got for f prime and you substitute c by 4, you're going to get this formula for f prime. Now you see that by doing it, initially I had the formula for f double prime by integrating once and using this piece of information that I have about f prime at 0. Now I have a formula for f prime. If I repeat this process one more time, if I integrate f prime one more time, then the derivative will be gone and I will have a formula for f. So let's do that. So from the previous page, we know that f prime is given by this formula. Again, what I'm going to do, I'm going to integrate both sides of this equality. So integral of f prime is equal to integral of this function. Again, so I need to integrate minus cosine plus 4. You know that so I put the minus sign aside. Integral of cosine is sine. This is again one of the formulas that we saw earlier today. And integral of 4 is 4 times x. Because if I differentiate 4x, I will get 4. And you can add any constant c. So integral of the right-hand side is given by this function. Now, how about the left-hand side? So you know that integration and differentiation, they cancel each other. So integral of f prime is equal to f. So this is equal to f, and that's also equal to this function that we have computed here. Now, what I'm going to do, I'm going to use this piece of information that I'm given. I know that f at 0 is 7. So f at 0 is 7, that's given. But then here, I'm going to substitute x's by 0. So f at 0 is equal to minus sine of 0, 4 times 0 plus c. So all I'm doing here is that I'm replacing x's by 0 there. And that's what I'm getting. And so again, we know that sine of 0 is 0 and 4 times 0 is 0. So the right-hand side, so these two terms will go away. In the right-hand side, you have c. In the left-hand side, you have 7. So that means that c equals 7. Now, if I go back and replace c by 7 in this formula, I will have a formula for f. So f is minus sine x plus 4x plus 7. So you see what we did here is that we were given the second derivative of f and the obtained f by integrating the f double prime twice, and every time we get a constant of an integration and use these given information to compute those constants. So this was the first lecture on integration. And for additional practice, you can take a look at the problems in section 5.1 of the Apex Calculus 2 textbook. This is a free textbook that you can download online. And for any additional help you may need, visit mathematicians.com. I will put the link for both these resources in the description.